All right, let's just dive right into this explainer. Today, we're unpacking the sheer engineering brilliance behind literally the heaviest structure on Earth. The Three Gorges Dam on China's Yangtze River is an absolute modern marvel. I mean, it holds world records for both its structural mass and its installed power capacity. But to really grasp the scale of what we're dealing with here, we actually have to look way beyond just the concrete and steel. We literally need to look at the planet itself.
To put this scale into perspective for you, look at this number, 0.006 microseconds. According to scientists over at NASA, the act of shifting 39.3 billion cubic meters of water up 175 meters above sea level to fill this reservoir, it actually changed the Earth's moment of inertia. The sheer concentration of mass in this one specific location shifted the Earth's rotational axis by about 2 centimeters. That actually extended our day by a fraction of a microsecond. We are talking about a human-made structure that physically altered the rotation of the globe. Insane, right? Now, looking at the raw numbers here, when you build a megastructure of this scale, standing 181 meters tall, stretching over 2 kilometers long, and demanding a staggering 28 million cubic meters of concrete, well, the laws of physics push back hard. All of this comes together to generate an unbelievable 22.5 gigawatts of power. But a project of this magnitude, which costs nearly $32 billion, by the way, doesn't just require building a wall. It requires completely conquering the very forces of nature.
Act 1. The wall. Conquering concrete and bedrock.
Okay, so to hold back the mighty Yangtze River, engineers had to create a massive gravity dam. This is a structure that relies entirely on its own colossal weight and friction to stay put, rather than transferring pressure out to the side canyon walls. But the very first hidden enemy they faced came from right inside the construction process itself. It's called the exothermic threat. You see, when cement mixes with water, it creates a huge amount of heat. If you just pour 28 million cubic meters of mass concrete and let it cure naturally without any temperature control, the thermal expansion would cause it to literally tear itself apart. It would develop these tiny microcracks that would completely destroy the structural integrity of the dam long before it ever held back a single drop of water. So how do you fix that? Well, to neutralize this exothermic reaction, engineers came up with a meticulously planned 3-step mass concrete cooling technology. First, instead of just using liquid water, they actually mixed the concrete with crushed ice. Second, they strictly maintained the ambient temperature of that mix at a chilly 7 degrees Celsius. And third, they embedded literal kilometers of cooling pipes directly into the concrete blocks, continuously circulating cold water to bleed that heat out from the inside. But of course, the challenges didn't stop at the concrete. They also had to deal with something called uplift pressure. Even resting on solid granite, water from that massive reservoir could seep into microscopic cracks in the bedrock right beneath the dam. That creates an immense upward hydrostatic force that could, no joke, literally float the dam right off its foundation. To stop this from happening, engineers drilled hundreds of meters deep and injected high-pressure cement grout. This created an impenetrable foundation grouting curtain that permanently sealed every single microcrack in the earth. Problem solved.
Act 2. The heart. Harnessing the mighty Yangtze.
All right, shifting gears from civil over to mechanical engineering, let's look at how this dam safely extracts an unbelievable amount of power. The beating heart of this power generation relies on 32 primary Francis turbines. The water violently drops 110 meters through these massive pipes called penstocks. Then it enters a hydrodynamic scroll case. Picture something shaped almost like a massive snail shell designed to perfectly angle the water right into the Francis turbine runner. This runner is a single moving piece of steel that weighs an astonishing 450 tons. As you can imagine, all of this spinning creates immense mechanical and magnetic friction. But that's safely absorbed by highly advanced hydrostatic bearings using closed-loop water and oil cooling. Each one of these main units churns out a massive 700 megawatts of power. But what happens when the river gets angry? When it floods, you have to be able to safely release that pressure. The dam actually needs to be able to discharge a historic 102,500 cubic meters of water every single second. Now, if that water just cascaded straight down the face of the dam, it would completely erode the concrete toe and the granite foundation underneath it. So instead, engineers designed a flip bucket spillway. This brilliant design actually launches the water high into the atmosphere, allowing it to violently break apart and dissipate its kinetic energy mid-air before it harmlessly lands far, far away from the base of the dam. Now, here's a problem you might not immediately think of: mud. There's a silent killer lurking in that water. The Yangtze carries an astonishing amount of sediment and alluvium every single year, which presents a fatal threat to the reservoir's capacity. Think about it. If left completely unchecked, millions of tons of river mud would simply stack up against the dam wall, eventually burying the underwater intakes and rendering the entire multi-billion-dollar structure completely useless. So how did they fix it? The engineers solved this with a brilliantly simple operational philosophy: discharge the muddy water, keep the clear water. During the heavy summer floods, when the river is churning and thick with heavy sediment, operators open up the bottom sediment discharge outlets. This allows that heavy, muddy layer to be physically swept right out from underneath the dam. Then, once flood season wraps up and the river runs clear again, they close those lower gates and capture all that clean water for power generation. It's so simple, but so effective. Act 3, the bypass. Lifting fleets over a 113-meter wall. So here is the ultimate logistical nightmare, right? You've just built a 181-meter tall concrete wall straight across one of the most vital shipping arteries on the entire planet. How on earth do you move massive shipping fleets over a 113-meter change in water elevation without bringing the entire region's river trade to a grinding halt? Well, the first solution is the world's largest hydraulic staircase, the 5-stage shiplock. To overcome this massive drop, engineers tapped into high school physics, specifically the communicating vessels principle. By linking 5 massive pools together, water just flows naturally from a higher pool to a lower pool until the levels equalize. Because they are just letting gravity do all the heavy lifting, they can raise fleets of massive cargo ships up the 175-meter total elevation using absolutely zero electric pumps for the water transfer itself. Zero. But wait, there is a catch here. If you just dump water into these locks from the top, you create a deadly waterfall effect that would violently crash those 10,000-ton ships right into the concrete walls. Nobody wants that. To prevent this, they designed a floor culvert system. The water actually fills from a grid of tunnels beneath the ships. It rises from the bottom up, completely evenly and slowly. This allows these massive vessels to be lifted 22 meters in just 15 minutes, while floating in total, perfect stillness. Now, what if you're in a hurry? For faster transit, engineers built a second bypass, the vertical ship lift. This is the largest mechanical lifting structure in the world, and it relies heavily on Archimedes' principle. Basically, a ship displaces its exact weight in water. So, whether a 3,000-ton ship enters the lift, or it's just filled entirely with water, the total mass of the chamber remains a constant 15,500 tons. Because of this constant mass, engineers could use perfectly matched massive concrete counterweights. This means the electric motors aren't actually deadlifting 15,000 tons. They're mostly just fighting friction and inertia. It is an absolutely elegant cheat code against gravity. And the way they actually move this chamber is wild. They completely threw out the traditional elevator cable system. Instead, the motors are mounted directly onto the chamber, and they physically climb the towers using a rack and pinion gear system. 4 independent pinion gears perfectly scale the 169-meter concrete vertical racks. And for safety, there are hydraulic safety nets that spin along with the lift. If there is even a millimeter of synchronization failure, these hydraulic valves clamp down and instantly lock the massive 15,500-ton chamber securely in place. So look at how beautifully these two bypass systems complement each other. On one hand, you have the 5-stage lock. It's slow, taking about 3 to 4 hours, but it offers massive capacity for 10,000-ton fleets, and it's powered virtually for free by gravity. Then on the other hand, you have the vertical lift. Sure, it can only handle 3,000 tons, but it offers rapid, mechanical precision, cutting that same journey down to just 30 to 40 minutes. Of course, you don't just build something this massive and walk away. It operates under immense scrutiny. Because the staggering weight of the new reservoir actually triggers small earthquakes, a phenomenon known as induced seismicity, the gravity dam was carefully designed to be flexible enough to withstand a 7.0 magnitude quake. To make sure this flexibility holds up safely, the structure is constantly watched by over 12,000 real-time sensors. They track everything from foundation pressure to microscopic expansions in the concrete itself. It's like the dam has its own nervous system. So, what does this all mean for us? The Three Gorges Dam is a brilliant testament to what happens when structural engineering, fluid dynamics, and sheer human will intersect. But looking at the scale of this, a dam that relies on perfectly balanced gravity, climbs vertical towers with rack and pinion precision, and, let's not forget, physically altered the rotation of the planet, it really leaves you wondering,
As we continue to push the boundaries of physics and scale, just how much further can our ingenuity actually take us? Thanks for following along with this explainer, and keep questioning the limits of what's possible out there.